box at the level C, it's possible to see this one in another two view. 1, 3, 3. And then in conclusion, what you see about it. In conclusion, we have a clear saturation that is present only at cortical level and not a peripheral level, obviously. And the equivalent current dipole show a very significant lateral displacement. What did you see about it? This is surely due to different neural groups involved in the response at the different intensity of stimulus, and probably at interference with motor activity. But in our maps, we didn't see ever quadruple structures. We didn't see ever a quadruple structure. It's probably due this fact at a different cortical size activated during different condition of stimulation. Thank you very much.
Thank you. Thank you very much, Dr. Persson, for your paper, which is open for discussion. Dr. Hamburg.
Yes, you showed now with, I presume, the magnetic data, the same thing that already is known for the electrical data. If you do somatosensory evoked potentials, as we, let's say, use clinically every day, then you see the same thing. But one important field is lacking in your data, which is the P26 or 27, the radial thing, because you see that what you showed is the tangential dipole, and just after this phase of tangential dipole, another it's turning around, and you see the radial dipole in the electrical data. And this might be due, and this would be interesting also to look at if that would be possible in your data, to perhaps, like Desmet thinks, two different groups of nerve fibers.
We now performed only the localization and the analysis of the very short related somatosensory 20 and 21 components, and we're going to perform also the localization and the analysis of the next epoch of the somatosensory exposition. I can do it.
If I may add a comment, we see it also in the auditory evoked magnetic field, that with increasing stimulus intensity, there's a certain saturation, but if you similarly record, or simultaneously record the electric potential, you don't see the saturation. So our interpretation is that since we only measure the tangential vector, obviously the overall vector may increase, but it's being rotated so that the tangential vector remains constant.
Actually, there is also, this is a partially answering your question. Of course, we cannot see these radially oriented sources. Yeah. So this, as you know, has been also discussed by John Desmet. This is certainly one of the arguments in favor of the existence of this radial dipole, because if we don't see magnetically, then it is most likely that it is radial. I mean, it's radially oriented more than the two tangentially oriented dipoles, one back and one in front of the rounding feature. But there is also another interesting findings which Marco Pereston has not yet shown, but I think that you can put the next slide. If you go ahead and you look at the next field distribution on this subject, which is at about 30, no, not the field distribution, the maps, about 28 or 30 is the second component. The next map. Prosegui con la latenza successiva. La stessa? Non l'hai portata? No, capito. Well, no. Maybe we can show later. And if you go to about 29 or 28, 29 milliseconds, the second big component, the nice thing, or surprising thing, is that the behavior is different. So this component is much larger, much stronger, below the motor threshold, and becomes smaller above the motor threshold. So this, in a certain sense, might be explained in terms of a reduction of the response at that latency, certainly due to a motor interference, because it is much stronger when you have only the sensitive level, but you don't have motor. You don't reach the motor threshold. If you reach the motor threshold, the intensity of this component goes down. So yes, we have observed this only in 2 or 3 subjects out of 6. So it does not seem to be a general behavior. But I think that later Marco can show this slide to you, if you like. It might also be gating. We have observed the gating, but it's a different experiment with a different paradigm.
Are there other questions to this talk? It's probably too early in the morning. Okay, in this case, thank you very much again. And we proceed to the second talk of this session. It's given by Dr. Pizzella. And the title has been slightly extended. It is now a normative study of somatosensory evoked field under median nerve stimulation and preliminary applications to brain plasticity.
Good morning, Mr. Chairman, ladies and gentlemen. I've added last sentence to my title, so now it's normative study of somatosensory evoked field under median nerve stimulation and preliminary applications to brain plasticity. The idea of this work was to investigate somatosensory evoked fields and look at these fields after strokes or after brain injuries to see whether the brain is reacting in some way and is giving somehow changing the way of functioning, having different groups of neurons being activated. So, first of all, to reach this target, we have to create a normative basis of somatosensory evoked field. Why somatosensory? Because they're easy to record and the amplitudes are high and no problems in field mapping and in source localization. So we decided to look at somatosensory evoked fields to left-right median nerve stimulation. So what we did actually was to simulate first, for instance, the left median nerve and then the right median nerve to record the field coming from this simulation and to perform field mapping and then source localization. this first was done on some normal subjects to see whether it was different localization between right and left side. And of course, the final goal is to investigate brain plasticity on patients who had suffered hemispheric strokes. So our experimental paradigm is to record these fields with these measurements are done with the 9-channel system we have in our institute, Istituto di Elettronica dello Stato Solido in Rome, Italy. I have one slide showing the system. Okay, is a homemade system inside a shielded room. It's working very fine. We have this system was originally designed to work outside a shielded room. So now that we have this opportunity to have the system inside, we are absolutely clear with no problem for artifacts 50 Hertz signals. And okay, so you can turn off the slides just to show you the system. The simulation of the median nerve was carried out just as Dr. Persons showed you before. Electric simulation at wrist and recording done on the head. We usually covered almost the whole head. We left out only the occipital region because it's the occipital region because it's not of interest, and also it's the difficult part to map, especially on patients. But anyway, in this case, we don't have problems because we can leave out this region without having problems in source localization. Usually we had 8 to 9 successive positionings, in one case 10, but anyway from 72 to 81 scalp sites. And the total recording time was about 2 hours, 2 hours and a half on special cases. I mean the whole session going from patient preparation to the end. This is a typical output. I've plotted here 5 out of the 9 traces I have from the system. We averaged about 450 trials, and you can see here at about 20 milliseconds the first cortical component. In this case, it's a little bit after 20 because this is an old subject. We were trying to also to have old subjects since we have to create a normative basis for investigating strokes. So usually we have old patients. And this is the N20 component, and I will focus only on this one. So I don't care about what comes next. This is just to show you the output of the 9-channel. The marker here is 20 milliseconds. So this is a different subject, a little bit earlier component. This is channel 1, just to keep trace of which is which. And the old epoch is 100 milliseconds, and the amplitude here is 400 femtotesla. And this is what comes out field mapping. This is again a normal subject. 15, 16, 17, we don't get anything really dipolar. we don't get anything really dipolar. And at 18, 19 start coming out, this dipole, and we have, in this case, just the maximum amplitude at the 20 millisecond latency, so just exactly that one. And this is done on the right hemisphere, so left simulation and right registration. Actually, we recorded the whole head also with left simulation. So we have also data from the left side with left simulation, but we just can't see anything because the dipole is, the generator is located in the right cortex. And this is the other side with the other simulation. So left side, right simulation. And again, I have this dipole here, and I can localize this as usual with the equivalent current dipole method. This, in this study, we use the spherical model, homogeneously conducting spherical model. Just with a little difference, these maps are drawn onto ellipsoids, and we fitted these ellipsoids inside the real head of the subject taken from MRI when possible, or with digitalization, three-dimensional digitalization. After that, I can fit this ellipsoid where I can draw my maps. To localize this activity, I have to fit inside this ellipsoid a sphere. And what I have to do is to take into account that some points may actually not be on the sphere, but a little bit far because of the ellipsoid. So the map here and is drawn on an ellipsoid, but the source localization self-procedure is done on a sphere. And this is what comes out in that case. This is my source localization. You can see this from front, from the right, and from the top. To have some numbers to compare to, I'm using this distance. This is the distance of the projection of this dipole to the outside, to the scalp here, the distance between this point to the vertex in centimeters. And this is the left-right displacement. In this case, I have the distance from the midline. This is the ear canal, this is a vertex. Okay, in centimeters again, then I can use the usual depth parameter. And you can see what comes out. Now I just superimposed the two localization from left simulation and right simulation. And what comes out is that there are some differences between the two parameters, T, P, and then the depth. Also, these are normal data. So this is just a table to summarize what I have from normal subjects. These two were left-handed, and seems that there is no difference between left-hand and right-hand subjects. Of course, we have only two, but we will increase the number. And well, these two were taken from Dr. Person's data, where he was actually simulating only the left median nerve. But anyway, since the setup is the same, I took those data in. And I have, these are the mean and standard deviation of these values: 7 centimeters displacement, 1.5 centimeters in front, and 3.1 centimeters deep from left, and from right they change a little bit, 7.7. The one which looks like it's changing a little bit is the frontal displacement. Now it's back to the occipital region, 2 centimeters, and the depth is fairly the same, a little bit deeper. So after that, we investigate five patients with ischemic problems, either on left or right, and in some cases with the complete recovery, we found actually good values within these normal limits, and in some other we had some different results I will show you now. So just to show you the traces for this is a subject, a man 75 years old who suffered an ischemic lesion on the left temporal and parietal lobe, and he had a complete recovery. So this is the N20 component I'm looking at, and after field mapping, this is the map at right lobe, and this is the left part, and you can see here the latency is a little bit different, but the dipolar shape is almost perfect as in normals, and the amplitude also of the signals is good, and the source localization was within normal limits. You can see this this picture. I superimposed the two sides, and see that also here we have this source displacement in front here and in the back, as in normals, I mean. And only the depth here looks like it's a little bit less. It's a rather shallow source, but within the experimental error. Now we come to a different patient who had much serious problems, and he had a large ischemic lesion on the left temporal, well, I would say the left hemisphere, and he had a complete occlusion of the left middle cerebral artery with no recovery and right hemiplegia. Lost my pointer, okay. And this is the good side, and the data are good. The dipolar looks fine, the amplitude is okay, and also the latencies, of course you can see it's almost 25 milliseconds, but we have also dealing with a man of 75 years, so this is possible. On the other hand, the left hemisphere showed no activity at all, and in fact this was the case. You couldn't move anything of the right part of the body. Well, maybe I can show you another case. This was a 77 years old man with the right parietal region, and he had the right a ischemic disorder of in the right middle cerebral artery about 6 months ago. And the CT scan showed this lesion, and he had a very poor recovery. This is again the good side, and you can see here the latency is 22 milliseconds, and the dipole is about where it should be, and the localization of this activity is also within our normal limits. I can show you this here. 3.2 centimeters stepped, and you can feel this from the other pictures. It's about where it should be. On the other hand, the other side showed an interesting thing. With this is 16 milliseconds after the stimulus, and going on, we don't see any real pattern, just very broad data, but with no clear-cut dipole structures. 23 milliseconds after, and then we can map after that. 24, 25, 26, 27, and you can see here seems like something is coming on very posterior region about 28 milliseconds after, and this was it's not really a dipolar shape, so we cannot talk about real source localization there, but there is some hints of a different brain site which is being activated now.